In this lesson we're going to look at electric fields, and first of all we'll define what an electric field is. So we've already seen fields in the area of magnetism. So you remember you can talk about a magnetic field, and that the magnetic field here is represented by these dotted lines. In this case, the magnetic field is the region around the magnet where a magnetic material or another permanent magnet can experience a force. Okay, so in the area of electricity or static electricity, which is what we're dealing with here, the electric field is defined as the region around a charge in which another charge experiences a force. So in the same way that we can depict the magnetic fields using these dotted lines, we're also going to depict the electric fields around a point charge. So the blue circle here represents a point charge, a negative charge, and you note that the electric field lines radiate out from the center of that point charge. Now that's quite easy to remember for your GCSE exam, but the tricky bit is remembering what direction the field lines point in what direction the field acts. You remember, going back to the magnet, you remember that the field lines always act or flow, so to speak, from north to south, from the North Pole to the South Pole of the magnet. So we can represent the direction of the field by these arrows, yeah? And in the same way we need to determine the direction of the field lines for a point charge, and that's quite easy to do. All you've got to do is remember this rule. Imagine you take a positive charge and you place that on one of the field lines, and then you ask yourself the question, in what direction will that positive charge move in this situation? Well, you know that positive and negatives attract, so we know that the positive charge will move in this direction, and that is the direction of the field. So we can say the direction of the field lines is the direction of the force on a positive charge. Yeah? And we can complete the diagram by including the arrows. So these will all be, so in this case the field lines will be pointing towards the negative charge. Now here we're talking about an isolated charge, right? A charge that is on its own and there are no other charges around it, so that this will have a radial field pattern. If we take another isolated charge, all right, I want you to assume that these charges are not together, they are separated by a great distance, right? So they do not interfere with each other. Well, in this case we've got a positive charge. Again, the same radial field pattern appears from the center of the point charge, but what direction do the field lines act in this case? Well, again, we apply the same rule. We place our positive charge on one of the field lines. We say in which direction will it move in this situation? Well, it will move away from the point charge because positives repel. So we know that the field lines will now point away from the positive charge. Okay, and that's the principal thing that you need to remember for your GCSE. Now, in the case of a situation where we have 2 point charges which are drawn near to each other, remember this charge here is just an imaginary point charge here, like this one. But in the case that I brought these 2 charges near to each other, well, what happens is that this radial pattern is then lost because these field lines, or the electric field produced by this charge and the electric field produced by this charge, will interact with each other, and so you get a much more complicated field pattern. Now, it is very unlikely, in fact I don't think you will be asked or ever asked in a GCSE to describe or draw or sketch that field pattern. You will only be asked to sketch a field pattern for a single point charge that is isolated. But in any case, we'll just have a quick look at the patterns that result. For example, here we have a positive and a negative point charge which are near to each other. Well, you can see, you know, what happens then is that the field lines get distorted in this way, and you get this kind of bunching up of field lines in between the positive and negative charges. So this looks a bit like a sort of hamburger. change that there. We've got the two pieces of bread and the hamburger in between, so it's kind of this kind of scrunching up effect. Again, the direction of the field lines, we want to quickly determine that using our rule. Again, we put our imaginary positive charge there. On one of the field lines we say, what direction will it move? Well, it will move away from the positive and towards the negative, so that defines the field line direction. That defines the field direction. So the field direction will be like that, right? Okay, and in the case where we've got like charges, well, the field lines will interact in this way. So here we've got two positive charges which are near to each other, and here we've got two negative point charges which are near to each other. Again, you can see in these cases that it's like the field lines kind of interact with each other in a way that they sort of repel each other. Okay, so rather than getting an intensification of the field between the charges, the field is weakened between these two charges. All right, likewise with the negative charges. Again, applying the rule, what way is the field acting? Well, we put our imaginary positive charge there. We say, what direction will it move? Well, we know it will move away from that positive charge, and so the field lines will move away from the point charge. Likewise here. And in the case of the negatives, well, it's going to go in the opposite direction. We've got the same field line pattern, but the field line directions are reversed. So it's very unlikely you're going to be asked to draw anything like this. It's a bit too complicated for GCSE. The next thing we need to do is look at the electric field pattern for a charged conducting sphere. So imagine that I've charged this sphere here, this conducting sphere, by induction with a negative charge. So there are negative charges with an even distribution all over the surface of the sphere. So these will be evenly distributed. That's important. Then what will be the resulting electric field pattern for that situation? Well, providing these are evenly distributed, which they will be because this is a conducting sphere, then we can assume that the field pattern can be constructed from an equivalent point charge at the center of the sphere. So we've got an equivalent negative point charge at the center of the sphere, and we can represent that by drawing the rays out from the center. So we would do that would be one of the field lines, and then there will be no field lines inside the sphere. So the field actually inside the sphere is 0, but outside the field lines would emanate as if they were emanating from a point charge positioned at the center of the sphere. Okay, and then we've just got to ask that final question: what is the direction of the field in this situation? Again, we do the same rule. We put our imaginary positive charge on one of the field lines and we say, which direction will it move? Well, the positive will be attracted to the negative, so it will move in that direction. So that sets the direction of the field lines. They will point inwardly, in this case, towards the center of the sphere. If the sphere was charged positively, then the field lines would act in the opposite direction. They would move outwards from the center of from the point charge in the center of the sphere. So the last thing you need to know is the electric field produced by a parallel plate conductor. Okay, so we've got this simple electric circuit here. We have these two parallel conducting plates, and we're going to charge them up using this circuit. So we throw the switch, and as you know, a current will then start to flow until the plates get charged up. What will happen is that electrons will flow from the negative terminal of the cell to this plate on the right, and likewise the opposite plate will become charged positively with an equal quantity of positive charge. So what we want to know now is, what will the field pattern, the electric field pattern, look like for these two parallel plate conductors? Okay, so the resulting field pattern will look like this, and let's just draw in the charges on the plates. One moment. So we've got the positive charges on the left hand plate and the negative charges on the right hand plate, and then just to apply the rule we put our imaginary positive charge on the field line and we ask what direction will it move in, and you can see that it will be repelled by the positive plate and attracted to the negative plate, so that defines the field line direction in the case of the parallel plates. They will go from positive to negative always. Now the key features that you need to note here is clearly that in the center of the plate the field lines are at right angles to the plates and parallel to each other, whereas as we move to the edge of the plates, either up or down, the field lines start to bulge outwards, and so you've got a kind of leakage of electric field here at the edge of the plates, at the bottom and at the top. Now you will not be asked to explain that, and all you need to do is to be able to draw the field pattern and indicate the direction of the field, and we're just going to leave it there for the time being.